Hello everyone. Let's begin with a fascinating thought. How can something smaller than an atom power entire cities? Welcome to the world of nuclear energy. When we look deep inside the nucleus of certain atoms, like uranium or plutonium, we discover a treasure chest of energy. For every tiny bit of mass lost during a nuclear reaction, Einstein's famous equation E equals delta m into c squared tells us that an enormous amount of energy is released. That's why nuclear energy is said to be 1,000,000 times more powerful than burning coal or oil. Truly amazing, isn't it? Now, let's move to the key principle, nuclear fission. Imagine a heavy nucleus like uranium-235 being struck by a slow neutron. It becomes unstable and splits into two smaller nuclei, releasing more neutrons and a lot of energy. One fission gives us nearly 200 mega-electron volts of energy, along with 3 neutrons. These neutrons can go on to cause more fission events, a beautiful chain reaction. But without control, it could run away into a dangerous explosion. That's why we need to regulate it with moderators and control rods. You can almost think of it like slowing down a bouncing ball before it causes chaos. Next, let's peek inside a nuclear reactor, the heart of a power station. We have fuel rods filled with uranium pellets, a moderator like heavy water to slow down neutrons, and control rods made of cadmium or boron that act like brakes, absorbing extra neutrons. All of this sits inside a reactor core, with a coolant like water or liquid sodium carrying the heat away. Picture the reactor like a carefully tuned orchestra. Each part has its own role, working together to keep the reaction steady and safe. As shown in the diagram, everything is encased in thick shielding to protect from harmful radiation. So, how does all this nuclear fire turn into the electricity that powers your light bulb? The answer is quite simple. The heat generated from fission turns water into steam. That steam spins a turbine, and the turbine drives a generator to produce electricity. It's actually very similar to a coal power plant, only here, instead of burning coal, the heat comes from splitting atoms. The law of power tells us that P equals W over T, or power equals work done divided by time. The faster and more controlled the turbine runs, the more electricity we get. Why go through all this effort? Well, the advantages are huge. A single kilogram of uranium can produce energy equivalent to millions of kilograms of coal. Nuclear plants don't release smoke or greenhouse gases the way fossil fuels do, so they are much cleaner for our environment. And best of all, unlike solar or wind, nuclear power runs day and night in all weather conditions. For countries with limited coal or oil reserves, it provides a powerful, reliable alternative. But of course, no technology is perfect. Nuclear energy comes with serious risks. We've all heard of accidents like Chernobyl or Fukushima, where radiation leaks caused massive harm to people and nature. Then there's the problem of radioactive waste. These materials stay dangerous for thousands of years, and safe disposal is still a global challenge. Not to mention, building and decommissioning nuclear power plants costs billions of dollars. It's a double-edged sword, powerful but potentially dangerous. Let's solve an exciting example to really feel the scale of nuclear power. Suppose 1 gram of uranium-235 undergoes fission. Step 1. We know 1 mole of uranium-235 weighs 235 grams and contains Avogadro's number of nuclei, about 6.022 times 10 to the power 23. Step 2. That means 1 gram has roughly 2.56 times 10 to the power 21 nuclei. Step 3. Each nucleus gives about 200 mega-electron volts or 200 into 10 to the power 6 into 1.6 into 10 to the power minus 19 joules. Step 4. Multiplying gives a total energy of nearly 8.2 times 10 to the power 10 joules. To put that in perspective, the same energy would require burning about 3 tons of coal. Incredible, isn't it? So to wrap up, nuclear energy is one of humanity's most powerful discoveries. By harnessing the mass hidden inside the nucleus, we can generate electricity at an enormous scale. But it comes with great responsibility, from managing radioactive waste to preventing accidents and misuse. In the future, scientists hope nuclear fusion, the same process that powers the sun, will give us a safer and cleaner energy source. Until then, nuclear fission remains a crucial but challenging pillar of our global energy mix. I hope you now see how splitting the atom can light up entire cities and also why it must be handled with care. See you in the next session with another fascinating journey into physics.